Hello again. In this topic, we're going to talk about extreme values. What that means is, if we think of the graph, how do we find the high points and the low points in the graph? And are there different kinds of high points and low points? And so we'll start with some definitions and then go through a little bit of theory so we understand what we're doing, and then some examples of how we can find absolute extrema on an interval. So first, let's talk about the different types of extreme values. We have what are called absolute extrema and relative extrema. Now, some textbooks are going to call them global instead of absolute and local instead of relative, but they mean the same thing. So here's what we will say. A function has an absolute maximum at some point C if the function values are less than the function at C for all x in the domain of the function. So what that means is it's the highest point on the curve for the entire function, as opposed to a relative minimum. A relative minimum at C means that the function, it's at its highest point on some neighborhood, near that C value. So what we say is the relative maximum at C, if f of x is less than or equal to f of c for some open interval about C. So we have to be able to look to the left and to the right of that C value and be able to tell that at C, the function is at the highest point nearby. Now, what this means, one thing that this means is that relative maximums cannot occur at endpoints of the interval of, let's just say, domain. Relative maximum cannot occur at the endpoints of a domain, because if we're at an endpoint, we can't look to the left or look to the right, depending on which endpoint we're at, to make sure that it is a maximum. However, the endpoints can give us global or absolute maximums. And then we have similar definitions for an absolute minimum. That would just be the lowest point on the curve over the entire domain. Or a relative minimum, the lowest point over an interval of the function. And again, relative minimums cannot occur at endpoints. So now, just to make sure we sort of have an understanding of these, let's look at this graph and try to figure out where there are any extreme values and what types of extremes. So let's first determine, are there any absolute maximums? All right, so absolute maximum, that would be the highest point on the curve over the entire domain of the function. Now, this graph just shows the domain from 1 to 8, right? That's the domain of this function. And what I see is that the maximum occurs, the maximum value is 6, and right, it occurs here and here. We can have more than one absolute maximum. So here's what we would say. There is an absolute maximum of 6 when x equals 6, x equals 8. Relative maximum. There is a relative max. Let's see, are there relative maximums? Now remember that relative maximums cannot occur at endpoints. So to me it looks like there are two relative maximums. There's a relative maximum of 4 when x is 2, and there is a relative maximum of 6 when x is 6. So relative maximum of 4 when x equals 1, and a relative maximum of 6 when x equals 6. Again, the maximum, the endpoint here cannot give us a relative maximum because it's not over an open interval. I cannot look to the right to make sure that it's the maximum. So it cannot give us a relative maximum. All right, minimums. How about an absolute minimum? So it looks like this one's pretty easy. There's an absolute minimum of 1 when x equals 4. Relative minimums. So looking at the graph, I see 2 relative minimums. There's a relative minimum at the previous point we mentioned, and there's another relative minimum here at, of 3 when x is 7. Again, this endpoint cannot be a relative extrema. So I have a relative minimum of 1 when x equals 4, and I have a relative minimum of 3 when x equals 7. All right, so there are some examples, just given a graph, of what we mean by absolute versus relative. So an absolute extrema can also be relative. Endpoints cannot give us relative extrema. Endpoints can only give us possibly absolute extrema. So now let's look at a few other situations and try and determine any extrema. All right, so the first 3 are all based on the graph of the function x squared. All right, so if we recall the graph of x squared, the graph of x squared looks roughly like this. Poorly drawn. Let's see, it looks something like that, right? It's that parabola opening up, right? So there's the function x squared. So if we were to just look at the entire function x squared, does it have any extrema? Well, we can see that there's an extrema here. I see that there is a local, sorry, I've been calling that, I got to make sure about my names here, right? So there is an absolute and relative minimum of 0 at x equals 0. But that's it. There would be no maximums to this function, because if we have if we look at the entire domain of the function, as we move far to the left or far to the right, the function continues moving upward, right, to infinity. There are no absolute or relative maximums to this function. However, if we change the function a little bit, if now we only look at the function x squared on the interval -3 to 3, well, that changes things. If we look from -3 to 3, we now have definite endpoints. And notice that f of -3 would be 9, and f of 3 would also be 9. So now, if we look at the curve over -3 to 3, that changes things like this. We would have, again, the same absolute and relative minimum of 0 at x equals 0. That would be the same. So I'll just sort of bring this down here. This would be the same. But now we have maximums. Now there is an absolute maximum of 9 when x equals -3 or x equals 3. Okay, now let's change it again. What if we now have the function x squared over the interval -1 to 2? Oh, I shouldn't have done that. All right, so now let's look over the interval -1 to 2. So now here's -1 and here's 2. And so we would have the point -1, 1 and 2, 4. All right, -1, 1. We have the point 2, 4. And those would be our endpoints for the curve. All right, what about our minimums? They wouldn't change. I'd still have that absolute and relative minimum. But now I would have an absolute maximum of 4 when x equals 2. And when x equals -1, we get the point -1, 1, but that doesn't give us any information. That doesn't give us anything new. So what we see here is by changing the interval over which we look at the function, we might change some of the absolute extrema for the function. Let's look at another example. Now we have g of x is the cube root of x or the cube root of x over an interval. All right, so recall that the cube root function does something like this. So if we were to look at the cube root function, does it have any absolute or relative extrema? It's always increasing, right? The cube root function always increases. There is no point on the curve where it changes to decreasing. So there can't be any places where there would give us an absolute maximum or minimum, or even local, a relative maximum or minimum. So this function has no extrema. However, again, if we change things up and say, well, what if we look at the function on -1 to 8? All right, so if we restrict our domain from -1 to 8, then we would have the points on the curve -1, -1, and we'd have the point 8, 2. Now, we would have an absolute maximum of 2 when x equals 8, and we'd have an absolute minimum of -1 when x equals -1. So again, by introducing a restricted interval, a domain on the function, we can now get absolute extrema. And so this actually leads to a theorem which we will not prove. It's called the extreme value theorem. And here's what it says. If a function is continuous over some given interval, then there must be c and d on the interval such that f of c is an absolute maximum and f of d is an absolute minimum. So if we are continuous over an interval, there must be an absolute minimum and absolute maximum on that interval. Whereas if we just look over an entire domain, we may not get absolute extrema. And so that's what we saw here. If we just looked at the function x squared, this had, for example, this had no absolute maximum, but the function x squared on -1, 2 had an absolute max of 4 when x was 2. It happened to occur at the endpoint. This did have an absolute minimum of 0, and this also had the same absolute minimum of 0. The function cube root of x had no extrema whatsoever. But the function cube root of x over -1 to 8 had absolute max of 2 when x equals 8, and had an absolute min of -1 when x was -1. Notice that both of those functions, x squared and cube root of x, both of them were continuous on that interval, either -1 to 2 for the x squared or -1 to 8. So then we ask, well, let's look at this other situation. Would we be guaranteed extrema for the function 1 over x on the interval -2 to 2? Think about that for a moment. Maybe draw a sketch and see what happens. So let's think of the function 1 over x. 1 over x does something like this. All right, there's the function 1 over x. And so if we look over the interval -2 to 2, that might be something like this. Here's -2 and here's 2. Are we guaranteed extrema? Well, no, because notice that when x equals 0, the function is undefined. There's a discontinuity at x equals 0. So, are we guaranteed extrema? No. There is a discontinuity at x equals 0, so we cannot apply the extreme value theorem. All right, so we have to be careful about situations like that. We have to check the continuity of the function before we try to apply the theorem. Now, if we go back for a moment to the x squared, notice that we did get an absolute minimum of 0, but it didn't occur at the end point. It occurred somewhere inside the domain, not at the end point, but somewhere in the middle of the domain. And it turns out that there's only specific places where extrema can occur on the inside of a domain. And this is one of Vermonts' theorems. So Vermont said that if f has a relative extreme value at x equals c, and if f prime of c exists, then f prime of c must equal 0. So think about that. What is this telling us? If there is an extreme value and the derivative exists at that c, then the slope of the curve at that point c must be 0. It must be what we've called a stationary point in the past, or a type of critical point. So notice, let's think about this again. If we think about the function f of x equals x squared, then the derivative is 2x, and 2x equals 0 implies that x equals 0. And notice that the minimum occurred at x equals 0. Now we've got to be a little careful with this. It doesn't guarantee things. So for example, the inverse of this theorem is not necessarily true. In other words, just because the derivative is 0, that will not guarantee a relative extreme value. If we think of the function x cubed, notice that f prime of x is 3x squared, and if 3x squared equals 0, that implies then that x equals 0. But if we think of the graph of x cubed, the graph of x cubed looks like this. Right? There's roughly the graph of x cubed. It flattens out a bit here when x equals, when x equals 0. Right? It flattens out, but it's not a relative extreme value. So, just because the derivative of x cubed at 0 is 0, however, there is no relative extreme value when x equals 0. Now, we're going to learn a technique later on that will help us understand how, after we find these critical numbers, how we can tell if they are relative extrema or not. We're going to learn that in the next topic. Sorry, not in the next topic, 2 topics from now. Also, we have to be aware that relative extreme values can also occur where f prime of c does not exist. If we consider the function the absolute value function is that v-shaped curve. Right? This is that v-shaped curve, and when x equals 0, the derivative does not exist because the slope on the left doesn't match up with the slope on the right. Right? That limit will not exist. So, and it turns out, and we haven't proven this, but if f of x is the absolute value x, it turns out that f prime of x turns out to be absolute value of x over x. Now, so notice that if f of x is absolute x equals 0 is on the domain, but f prime at 0 does not exist. So that means that x equals 0 is a critical number, but f prime of c is not 0, and we can certainly see that there is a minimum at x equals 0. All right, so we have to be aware that extrema, relative extrema, can occur also at places where the derivative does not exist. Okay, so a couple of things to be aware of. All right, so that's most of the theory behind this topic. And now what I'm going to do is I'm going to stop this video, and we're going to start a second video that's going to go through examples of finding extreme values, extrema, for a function on a closed interval. All right, so I'll see you there.